Hello, ladies and gentlemen. This is your science teacher, Mr. Tao. And today what we're going to do is we're going to look at how stars evolve from the time that they first come into existence until the time that they finally expire at the end of their lives. So, as we can see here in this diagram, we've got a diagram of stellar evolution. This is very similar to what's been on the Regents. In fact, you can find it in your review book. Its similar diagram is on page 43, and that diagram actually comes to us from an old Regents exam. Basically, stars start out in the beginning with this nebula, which is just a cloud of gas and dust, and they take one of two paths, right? So the first possible path is that they go over here and they become an average star, right? If it's not a very big dust cloud, it doesn't have a lot of gravity associated with it, then it just becomes an average star. So this is like our sun. Our sun is just a middle-aged average man, kind of like your teacher. So then we go over here to later in life, and it becomes a red giant. We'll talk about why that is. And then after the red giant phase, it becomes a planetary nebula. And this word nebula here just means gas and dust cloud. A stellar nebula is at the beginning of a star's life. A planetary nebula is at the end of its life. So when we see this planetary nebula, what this really is the gas and dust that was inside of this red giant here, but the shell is gone. And all that's left is that little tiny dot there, very bright, very dense, which is the remnant core of this object. Eventually this dust cools off, and when it cools off it becomes dark and we can't see it anymore, and then we are left with a white dwarf. Ultimately a white dwarf will slowly fizzle out and become a black dwarf, at which point we can't see it anymore. It still has a gravitational pull, but we can't see it anymore. If we go this route down here, right, so now I'm talking about the bottom half here. If we go this route, down this way, first, a massive cloud would become a massive star, massive blue star. And these stars burn very hot because they have more gravity. Because they have more gravity, there's more compression. More compression means more friction. And they burn the fuel faster. In this case, this guy here will become a red supergiant, and then it ends with this giant supernova explosion. So our sun is not going to have a spectacular fireworks show at the end. Instead, it's just going to collapse. But these stars explode, like what we saw in the Crab Nebula. The Chinese actually documented this in the 12th century, where they witnessed a explosion in the sky over a period of several months, and that's the Crab Nebula that we see today. But this supernova explosion occurs, and then one of two things happen. If it's a smaller massive star, it'll become a neutron star, and it just kind of pulses and blinks. This thing has a very high density, which is why we call it a neutron star. It's composed almost entirely of neutrons. The neutron is a proton and electron together. It's a neutron star, very high gravitational pull, which is the reason why the proton and electron are fused into one. We see it blink because light actually has a hard time escaping the gravitational pull, and usually they're rotating very fast. If it's a most massive star, it could become a black hole near the end of its life. And the only way that we know that black holes exist is by the radiation that they emit. So let's go on to the next slide. So most stars start off as blue and then they become red. We talked about that in class before. As they age, they go from blue to yellow to orange to red. Okay, these large stars are called giants or supergiants, and we can see them on page 15 of our Earth Science reference table that we'll look at in just a little bit. Supergiants end their life as a violent explosion called supernova, and it results in a neutron star pulsar. that could become a black hole. The giant stars, when they end their life, okay, the shell of a red giant can collapse, leaving the core star behind, which is a white dwarf that eventually becomes a black dwarf. And that's just the core. So when we see the evolution of stars, this is a very fancy Hertzsprung-Russell diagram. You have something like this at the end of your reference table on page 15, not in color like this, but this is nice because it's colorized, right? On your reference table, you're going to have colors down here in this area. And as you can tell, color is directly related to temperature. So the more blue it is, the hotter it is. The more red it is, the colder it is. Our sun is right there in the middle. See it? Right there. Average, everyday kind of star. And this is called the main sequence. And what these stars are doing is they're taking lighter hydrogen, which looks bluer early in their life. Most stars early in their life are over here, right? So this is where they are when they're early. And as they age, they fuse more and more hydrogen into helium. Helium is a yellower element when we talk about the electromagnetic spectrum, and therefore they get more of a yellow appearance. And eventually the helium will be fused into heavier elements like carbon and oxygen. So C and O fusion occurs down here. We'll save that for an astronomy course, but that's the reason why they turn red, or one of the reasons why. So this is the path that most stars take. It's called the main sequence. There are a few random stars up here in the top of this, as we'll see. Those are just our supergiants. So what happens? Okay, a star has a core, and what happens is down here when a star first forms, the core initially is forming, and it's not quite as hot in the very beginning, the core that is, but because the solar envelope, that's this area right here, see this right here? That's called the envelope, right? It's that yellow space between the core and the shell. That distance is very small in a early formed star. This distance I'm shading in right here. For that reason, the core is very hot, but the distance is very short. So what that means is that there's a lot of heat transferred to the surface. So there's a lot of heat here. This guy is very hot on the surface, right? As the star ages, its core becomes smaller because in hydrogen fusion, we take 4 hydrogens and we make it into 1 helium. So the sun right now is taking 4 and making 1, taking 4 and making 1. But what that means is that the size of the core is getting smaller. As it gets smaller here and here relative to its size, relative to its overall size, the core gets hotter. And because the core gets hotter, it pushes that heat energy out here. And as it pushes the heat energy out there, it makes the star expand in size, such that way out here, we're now so far away from the core that the surface is cooler. And when it's cooler, the color is more red. So remember, this is going to be hot. This is going to be blue. And again, the reason why it's hot is because the solar envelope is kind of small. This solar envelope, not a lot of distance there. Why is it small? Because the core is cooler. this core right here is cooler. And as we go this way and it ages, what ends up happening is the core gets hotter, but the surface gets cooler. Let me say that one more time. In the beginning, the core is cooler, but the surface is hot. Out here, in this area, right, the core is hotter, but now the surface is cooler. The opposite has happened. Okay, so here we have another expansion to a red giant. And just what happens here again, this hydrogen is fusing, the core is shrinking on itself. As it shrinks and compresses, it gets hotter. And as that gets hotter, what ends up happening is it pushes, literally just pushes the shell of this thing out because that core is getting so hot, right? Like this. Okay, so what's going to happen to our sun, right? Let's go ahead and take a look at what's going to happen to our own sun. So this is an animation that I have here. And in order to play this, you have to have Internet Explorer turned on. So I'm going to go to Internet Explorer. And let's go ahead and I have it open down here. It will not play in Chrome, and it will not play in Firefox, to my knowledge. This is the future of the sun. So we got the temperature on Earth, and we can play this, right? You can also play this on your own when you view the PowerPoint later. But you can see the sun is slowly growing in size. Here we are 3.2 billion years in the future. This is in Kelvin and Celsius right there. All right, average temperature on Earth, 4.5 billion years from now, average temperature on Earth, 213 degrees. Probably not going to be so good for life. And the reason, again, is because the sun is getting larger in size, which means that we're closer to the surface of it, right? So we're hotter. And then all of a sudden at the end, it gets really big near the end. And look at that. At this point in time, average temperature on Earth is going to be 969 degrees Fahrenheit. Definitely no life. 6.2 billion years in the future. And then what happens? The sun just fizzles out. And in reality, if this animation was correct, there would be no Earth, because it will probably vaporize the Earth in that process. So, but that's a long ways away. We don't have to worry about that right now. So going back to where we were in our presentation, we stopped right there. So apparent brightness, we talked about this before, right? The more distant a light source is, the fainter it appears. Just because it is more distant doesn't mean it's brighter. Sirius is the brightest star in the northern sky. The only reason it's that bright is because it's so close. It's only 9 light years from Earth. It's not the biggest star or the brightest. It's apparently the brightest. So Sirius I like to think of as the kid on the bike here, who seems very bright, even though we all know the bike light is not that bright. It just seems bright because it's close to us. So here's our star chart, right? So we've got main sequence stars here. I've got color and temperature at the bottom. I've got the size of stars on the right. And I've got their luminosity or brightness on the left. So you can see here that the really what comes down to is very important. The more massive they are, the brighter they are. So let's go ahead and see if we can do a question together a minute, shall we? Let's do a question that is at the end of this section. So I'm going to go back to Moodle right here, and I'll do a question with you, and then you'll be able to go back and answer this on your own. So let's hit next. Okay, as a star changes color from blue to red, surface temperature of the star, blue to red, definitely decreases. We'll hit submit. And that's on the reference table, page 15. You can see that on the bottom of the reference table right here. Blue to red. See it? And it gets cooler. All right, well, that's all I have for now. I want you to go ahead and try the rest of these questions on your own. And good luck. If you have questions, be sure to ask me in class.